So in this case, how do you solve for x when it's x squared minus 2x minus 3, Chelsea?
You can factor it and make it x minus 3 times x squared.
So the only way you're going to get the x of a denominator that has an x squared in it is to solve for x, and the way we solve for x will be by factoring. Or using completing the square, or the quadratic formula, or synthetic division. We now really have a whole bunch of different ways to solve for x. So in this case, we know that x is not allowed to be 3 because it makes the denominator undefined. And it's also not allowed to be negative 1 because, again, that makes the denominator undefined. And when the denominator is undefined, that then creates the domain, and it gives us those intervals for us to use. So for f of x, the domain would be from negative infinity to negative 1, negative 1 to 3, and 3 to infinity. Because there are two different numbers that would make the denominator 0. What's the domain of g of x? Chelsea?
Negative infinity to 3 and then 3 to positive.
Nice. Because there's just x minus 3 in the denominator, so x can equal 3, which creates the domain negative infinity to 3, 3 to positive infinity. I'm going to skip the next part for this just for a minute. And you were asked to make a table. And that table is just by using the two equations, plugging in values, creating numbers for negative 2, negative 1, 0, 1, 2, 3, and 4. Alice, do you have the f of x values for your table?
Yeah, so I got negative 1.
When you plugged in a negative 2?
Yeah.
Feel like it's supposed to be a fraction.
Maybe I switched g of x and f. 3 to 2 is a
It's, say again?
3/5.
3/5 is
I
right.
think I switched them. You switched the negative. No, I switched the f of x and the g of x. And that wasn't correct.
What'd you say?
2 is negative 1. Yeah, positive
2 is negative 1. What do you have for negative 1, Alice?
1/2. Wait, I don't know.
Okay, maybe I'll pick on somebody else.
Virginia,
Virginia, what do you have?
For f of x, we have 3/5 and then error,
So undefined if there's an error.
and then 1/3, 0, negative 1, undefined, and 3. And then
Alice, did you have any of those?
no,
Yeah? Okay.
they're just I don't really have them. They're in some weird order.
Okay. Okay. And then for g of x, it should be
The same thing.
except,
Negative 1 is 1/2.
right, negative 1 is 1/2. That's a 5. So for g of x, you should have the same y values, except at negative 1, you have the value of 1/2. It's still undefined at 3 because we said x could not be 3. And then when you plug in a 4, you end up getting 3. So for all of the values from f of x, they're exactly the same as g of x, except at the value of negative 1, you have an answer because it's allowed to be negative 1 in the g of x function. So the next part of the question said to use your calculator. Trying to find the directions here. Use a calculator to graph f and g, and then explain why there are differences in the graph of f and the graph of g, or the domain of f and the domain of g. So that was kind of what it was asking you to do. So instead of graphing on my MacBook, because it doesn't like me today, or ever, essentially, I have a graph on my calculator. So if you could, in your calculator, just plug this in, kind of see what happens with the graph. How many graphs should you have? 2, right? I mean, you have 2 different equations. When you graph it, you should have 2 graphs. So this is what my graph looks like. There's a vertical line going down my graph. What's that vertical line represent? An asymptote. So my calculator is old. And the old calculators actually drew in the vertical asymptotes, which in some ways was kind of nice because then you could see quickly identify where the vertical asymptote is. And then in other times, depending on how crazy the graph is, it got in the way. But that's the vertical asymptote at x equals 3. However, Chelsea just told me that there was supposed to be another one at -1. So that means you should have another vertical asymptote at -1. But there isn't one there. There's just the vertical asymptote at x equals 3. And the problem wanted you to kind of decide, why is that happening? So even though our problem for f of x shows that there should be two values that x cannot be. Therefore, if x can't be those two numbers, you should have two vertical asymptotes. And the question is, why is there only one? So if you look at the problem, the original function for f of x, does anybody know why there is just the one value?
So it's not an asymptote because it doesn't get skip along it.
In the graph, it doesn't skim along it. Cuh? So if you look at the top, it currently is x squared minus 1, which can factor as x plus 1, x minus 1. Do you mind doing that? Thank you. And the bottom, Chelsea factored for us as x, thank you, minus 3 and x plus 1. And then Cuh said, after you factor them, you can sit in the back. Thank you. So Cuh, what happens after you factor them? Yeah, so x plus 1 is common to both. And because it's common to both, that term cancels out. It vanishes, it disappears. And what you're really left with is x minus 1 over x minus 3, which is identical to the g of x function. That's why it looks like there's one graph when you graph it, because they're exactly the same equation. That spot where you have that piece canceling creates a hole in your graph. So the part that vanishes away, literally that point vanishes from your graph. And there's a little hole sitting in the graph, but you can't see that little hole in the calculator, because even though my calculator is old, your calculator is new, it still doesn't have the power to actually draw a little circle. It would be like an open circle in a graph if we could draw an open circle. So at the value where x is -1, if I go to my table of values, when x is -1, there is an error in the f of x function. That's my y1 function, because it still can't be -1. Because if it starts somewhere in the equation, even though it might cancel out because we simplified it, it still is in the initial part of the problem. Brandon?
So it quickly disappears and then continues backward.
Exactly, yes. So it disappears at that one little point and then continues moving on the same pattern that it was moving on. So that one space at -1 is gone, vanished, and then it just continues moving on its path. So a hole in the graph, we would have a vertical asymptote for f of x at x equals 3, but we would have a hole in the graph at the piece that canceled, and that would be at -1. So a hole happens when a function is simplified, and that piece that simplifies or cancels from the equation creates the hole. An asymptote is still that end result. So if I look at the two end answers, they both have the same vertical asymptote at x equals 3. Because in the end, after they're simplifying, there still is an x minus 3 in the denominator. So that part is still the asymptote. But the first one gets a hole in the graph because of that one piece, that one factor canceling out.
So whole is when a problem factors, and asymptote would be that end result, what's still left in the numerator or the denominator. Nice job, Cut, for noticing that. Good job. Anybody else notice that? Thanks, Michael. Good. So it's kind of different to have that piece happen. No, like that wasn't in any of the notes that we would have done, even if we would have got through all 4 of those examples yesterday. That was not in any of them. It was just something for like you to try and see, can you think about it, what's happening, can you figure out what's going on with that initial function. So as I said, 29 was very similar to that problem, except 29 ended up being a line when you graphed it. So I want to talk about 48 as well, but are there questions with like the difference between a whole and an asymptote? So if you look at 48, is a little, it says biology, but Katie Emmons said that in apes, anybody in environmental science? Oh, yeah. Did you talk about deer and apes?
Oh, I'm in honors.
Oh, you're in honors. You haven't talked about deer yet.
No.
Maybe you need to ask. Find out about deer. Apparently in AP environmental science, which she said too much homework, so it's good you didn't take it. Yeah, good to know, right? They were talking about deer population, especially in the North Hills of Pittsburgh. But this one here says the Game Commission introduces 100 deer into a newly acquired state game lands. And of course, like the deer are going to stay in this area because that's what they do. Like North Park, like you create some deer, you drop a population of deer in North Park, and they're just going to stay in North Park and not venture anywhere else because it's not fenced in. But the population is given by N, which is the number of deer in our herd, so the number in the population. And then it says 20 times 5 plus 3t over 1 plus 0.04t. And then it says t is greater than or equal to 0. So t is time, n would be the number of deer in the herd, and the time is in years. So I want you to plug this in your graphing calculator just to see what the graph looks like. But the only part that you really need to focus on is this piece right here. Did anybody graph it in the calculator and maybe draw yourself a little picture? Chelsea?
I did.
What does it look like? Yeah, like a little, like, I don't know, hook curve, kind of like this, right? And then there's another part over here, but we don't really care about this part because that's when t is less than 0, and we don't need to know when t is less than 0. So it's like a little hook part here. So that's what the graph looks like. So part B says find the population when t is 5. So after 5 years, what's the population? After 10 years, what's the population? After 25 years, what's the population? Which you can do just by plugging in 5, 10, and 25. And the goal is for you to see how much it increases. So after 5 years, it's now at 333 deer. So it started with 100. 5 years later, we're at 333 deer. 10 years later, we're at 500 deer. 25 years later, we're at 800 deer. So you can see that it definitely increases as time goes on. But part C is the part that I thought was interesting. Because again, it makes you kind of think about what does it really mean when you have numbers in a problem that really refer to a real life situation. What is the limiting size of the herd as time increases? So remember that the x-axis is really t. So as time goes on, what is the y value? Or, in this case, the number of deer. Is there a max value? Well, if it's curving and eventually kind of just leveling off horizontally, there has to be a max value because it's not going to increase. But what in the equation would force there to be a max value? That's really what the question is kind of asking. So why would there be a maximum value? Virginia? Right, there's a horizontal asymptote. So somewhere in the graph, there's a horizontal asymptote. And that horizontal asymptote is like your boundary line. It can't go beyond the boundary line, above the boundary line. It's limiting itself to that boundary line. In that equation, where would you find that? Or how would you find the horizontal asymptote? Do you know, Virginia?
I multiplied 20 times 3 to get 60, which I divided by 0.04.
So we have this equation. She said she distributed the 20 through. And then because the powers are the same, your asymptote is found by taking the coefficients, which would be 60, and dividing it by 0.04. And then Virginia, that number for a horizontal asymptote would be 1,500. So that's where the horizontal asymptote would be. That means that's the max value for the number of deer in this population. So eventually, after so much time, as time goes on and on and on, and I mean, it'd have to be beyond 25 years, because at 25 years, we're only at 800. So this is like a way long time from now. We get to a point where you can't really have any more deer. So you're going to have the same number die and the same number that are born the next year, and those numbers are pretty much going to even out. But that's because of the asymptote in the graph. So an asymptote creates like a max value. We're no longer dealing with parabolas or polynomials where you have those max curves. So when we're looking at a function and it's a fractional function, a rational function, the asymptote creates the max value because it can't go above that asymptote. So 1,500 deer. It's a lot of deer for one area that are supposedly going to stay in this confined game land. Does anybody think like deer in your backyard, or is it just my backyard? Yeah, they're all over the place. It's crazy. We have people down the road from us that feed the deer, which probably doesn't help. Like, who feeds deer?
Old ladies.
Yes, crazy old ladies. Yes. Don't feed deer. They eat my plants. So you'll have to ask, because they were, I guess, talking about ways to get rid of deer. No, you don't want to find out? No, you won't ask. See, I'm trying to tie in the environmental science and the math. We've got a question that ties them both in together. Isn't that great? Yeah, we'll be tying in physics too. Yeah. I promise the English, I'll just leave that to Mr. King. Yeah, just leave that to him. So today we are going to analyze graphs of rational functions, which pretty much kind of talked about yesterday. But if you were unsure of some of the concepts yesterday, how to find the information, we'll go through it today and then actually make a shape of the graph. So you will be graphing today. You'll need a calculator to kind of finish the shape of the graph. Unfortunately, I mean, we could do these by making a T-chart, but if we have the technology to help us, we might as well benefit from the technology as well. So just like synthetic division and the finding all the zeros, we have the technology. We're going to use the technology to help us, but we'll have a little bit of algebraic support. So in your packet, this is section 2.7.
You really didn't want to have to say when you have to use the calculator.
So 2.7 is really two different parts. Today we're going to look at functions that have vertical and horizontal asymptotes. We'll talk about getting the intercepts of those functions, and then we'll talk about graphing. Tomorrow we'll talk about slant asymptotes. So asymptotes that could go diagonally, which we didn't get to talk about last year, because you need to know how to divide in order to use slant asymptotes. So we'll talk about slant ones tomorrow. And then test on Friday. Sorry.
Oh, that's good. And then the physics test and the math test.
All right, so little bit of review, kind of summarize the material from yesterday. To find a y-intercept, you said x equals 0, which you've been finding x and y-intercepts probably since Algebra 1. In some form, based off the equation, it does get a little more involved the higher you go. So we're setting the x to 0 to find the y-intercept. To get an x-intercept, you set y to 0, which in our case, really it's the numerator we're setting equal to 0. So the numerator is going to equal 0 because that's the part of the problem that finds an x-intercept for us. The denominator is the part that gets the vertical asymptote. So the numerator finds the x-intercept, the denominator finds the vertical asymptote. And then the horizontal asymptote is one of those three rules. So if the powers are the same, like the problem we just did, we can use the coefficients in front. If the number on the top is smaller than the one on the bottom, so if I have an x compared to an x squared, then it's y equals 0. And then it's the other way around. If you have an x squared on the top and an x on the bottom, then there is no horizontal asymptote, and that's where the slant one comes in. So we're going to try and graph all that information, use the graph to help us get a guide as to what the graph should look like, and then we'll rely on the calculator to help finish the graph. Some of them you might not have to, but others you might. So, looking at letter A, we have 2x minus 1 over x. I'm going to just find those 4 pieces of information, try and use that information to help us get a graph. I need to see a little bit of work, even if it's just showing me what you did, like by plugging zeros in for x, by plugging a 0 in for y. I just need to know where your numbers are coming from, instead of just like relying totally on the calculator. So y-intercept, we're finding the y by plugging 0 in for x. So Brandon, what happens with this one?
You can't do it
Why not?
because you can't divide by 0.
Right, we end up with -1 divided by 0. What's that mean about the y-intercept then?
There isn't one.
There isn't one. So there is no y-intercept. Make sure you write none, or that it doesn't exist.
With undefined.
Undefined words. Yeah. The x-intercept, so now we're taking the numerator, only the numerator, setting it equal to 0. And this should be written as an ordered pair because it is a point on the graph. So Chelsea, that point on the graph exists at 1/2 and 0. So intercepts are ordered pairs. Asymptotes are lines, so they should be an x equals or y equals 4. The vertical asymptote, there's just an x in the denominator, so the asymptote happens at 0. That's the place it's undefined, which is why the asymptote is there, because it can't touch that vertical asymptote. And then how about the horizontal asymptote? Brandon?
2,
Why 2?
because you're taking 2 divided by 1 since the powers are the same.
Yeah. So looking at the powers, you have a 2x on the top and x on the bottom, so then it's just y equals 2 over 1 or y equals 2. Questions? Okay, so we're going to plot this information. You have a nice graph. I'm going to draw a couple of tick marks on mine. So 1/2, we have an x-intercept. That's the only point that we have. But we do have a vertical asymptote at 0. We draw vertical asymptotes as dashed lines. That is, no, they're not actually part of the graph, but they're boundaries for our curves, and our curves skim along those. So we'll use them to help us create the graph. And then the horizontal one, y equals, again, make sure you have the correct notation. So it is a line, that's why it gets y equals. It's not just the number 2. So without going to the calculator, using a little bit of what you know about graphs. A graph has to cross through the x-axis if there's a point on the x-axis. And then the graph approaches the asymptotes and skim along the asymptote. So here's my x-intercept. It has to approach the asymptote and skim next to it. It never goes over it. It's just going to skim along that asymptote. And then, again, it's going through and skimming next to it. It shouldn't touch it like mine did. Pretend mine didn't touch the y-axis there. It should skim next to the y-axis. Where do you think the other one would be?
There.
Yeah. So if there's just one intercept, or I'm sorry, one asymptote, generally you're going to have that other piece of the graph diagonal. So that other piece of the graph would be up here. So there is some symmetry. There's symmetry with the asymptotes, but they're not really symmetry with the origin, symmetry with the y-axis. So you can check the graph in the calculator if you want. This one is kind of a basic one just because all the powers are 1. The lower the power, the more basic the graph that you're working with. I know this isn't on there, but domain and range are going to be things that you'll be asked about these functions. So just to make sure everybody's comfortable with domain and range, which asymptote creates the domain? Chelsea? The vertical asymptote. So the vertical asymptote will always force your domain. Whatever the asymptote is always in the domain. So it's at 0, so negative infinity to 0, and then 0 to infinity. The range sometimes goes with the asymptote. Sometimes it just depends on what your graph looks like, which is why the range, we kind of use the graph, especially as the graphs get a little more involved. This time, the graph is a basic graph, and it is exactly with that horizontal asymptote. So negative infinity to 2, and 2 to infinity.
Questions? So we'll see if we can look at another one, just to get extra practice working through another problem that's a little more interesting because the power in the denominator is now x squared. So see if you can work through those pieces of the problem. Libby, what do you have for the y-intercept?
I have 0, 0,
And the x-intercept?
0, 0.
Yeah. How do you think you'd find the vertical asymptote?
And just be 0. Or no, wait.
So if we set the denominator equal to 0, how would we find the vertical asymptote?
We make would you complete the square?
You could complete the square. What else could you do?
Quadratic formula.
Quadratic formula. What's my favorite F word? Factor. We can factor. This one does factor. So yes, you can complete the square. Yes, you can use the quadratic formula, but factoring might be easier. Brandon, how would this one factor?
X minus 2x plus 1.
So -2 and +1 combine to be a -1. So by factoring the denominator and setting them equal to 0, you then can find your vertical asymptote. So 1 is a +2. There's a second one at -1 since there are two factors in the denominator. So by factoring the denominator, we end up finding vertical asymptotes. And then the last one, Michael, where would the horizontal one be?
Oh, it's 0.
Why?
Because the denominator, the degree of the denominator is greater than the numerator.
Awesome. So degree of the denominator is bigger than the one in the numerator, so it's just at 0. So graphing this, you have one intercept again, but now we have two vertical asymptotes and one horizontal. So intercept 0, 0. And then -1 for an asymptote and +2. And then y equals 0 is another asymptote. That's our horizontal asymptote. It is okay for the graph to go through the horizontal asymptote in the center of the graph. So that might happen depending on how many asymptotes you have. The ends of the graph are the part that'll skim to negative infinity and positive infinity. That's the exception, yes. So that center, and it's always like in between two asymptotes where the exception will occur. So it'll be in the middle of the asymptotes. So it's a rule breaker. That's what Sadie, my younger daughter, she's like, oh, I don't like that word. It's a rule breaker. Kind. K-I-N-D. She's like, it should be kin, Mom. I'm like, I know. It's kind. I don't know why. It's a rule breaker. English breaks a lot of rules. All right, so I would suggest you taking a peek at this graph in your calculator. Kate, I think you took a peek at it, yes? No? Oh, I thought you did. Chelsea? Okay, on the left side of the asymptote, what's happening over there?
It goes like this in the third quadrant.
In the third quadrant, yeah. So something like this. Use your asymptotes to help you make a graph. In the middle, Chelsea, what's it doing?
It's like a backward X.
Yeah. So decreasing from the left asymptote to the right asymptote. And then on the right side of 2 is
It's in the first quadrant.
up here in the top, first quadrant. Does this graph have symmetry? Is it symmetrical in the y-axis? Does the y-axis cut it in half? Does the x-axis cut it in half? No, because that would mean this piece here has to be up here as well. So you'd have to have this piece symmetrical right above it so that it's kind of a flip. And it doesn't have original symmetry either because these two asymptotes are not proportional. You don't have one at -2 and one at +2. There's one at -1 and one at +1. Questions? What's the range of this graph?
Oh, but is there a point at 0?
Yes,
Yeah.
so negative infinity, positive infinity.
Yeah, negative infinity to positive infinity. So even though you have these two curves, those are curves, are called branches. That middle part touches 0. So it kind of like overrides the other two curves, and the range would just be from negative infinity all the way to positive infinity, because that center part's touching everything. The domain is going along with the vertical asymptote, so negative infinity, -1, -1, 2, and then 2 to infinity. But the middle of the graph, make sure you're checking that middle to look for the range, because if it goes through the whole graph, then the range is negative infinity to positive. Questions? So one more. We have h of x equals 2 and then x squared minus 9. You might want to make it x squared minus 18 just to help you get those asymptotes. The x-intercepts might be a little easier to just distribute it through, especially with the horizontal asymptote, remembering that that affects all parts of the graph. So a y-intercept would be 2 times 0 squared minus 18, and then 0 squared minus 4. Anyone have the y-intercept? 9 halves, yeah. So it's negative 18 over negative 4, which is 9 halves, not 9 fourths. And then the x-intercept, so take the 18 to the other side, divide by 2. We're looking at x squared equals 9. So what are the x-intercepts?
-3, 0,
And then 3, 0. Nice. Now we have a lot of points. And all the other ones we had 1, and now we have 3 different intercepts. So the vertical asymptote, setting the denominator equal to 0. Virginia, what would the vertical asymptote be? Nice, -2 and +2. And then the last one, how about the horizontal asymptote? Looking at the powers. Here we go. Brandon? Yeah, y equals 2 because it's 2x squared and 1x squared. So the powers are the same. It means the asymptote would be the coefficients, and that's just 2. So lots of things to graph. 9 halves is really 4.5. Graph your two ordered pairs for the x-intercepts at -3 and +3. And then the two asymptotes that are vertical. So we know it has to go through the two intercepts, which mine just missed that first one on the left. So you got two bottom pieces, and then the middle piece is kind of like a parabola that goes in between the asymptotes. And I'm just going to quickly talk about the range of this one. It's -∞ to +2. What's the other part of the range?
9 halves.
Yeah, or you could say 4.5. 9 halves to +∞. Michael, what goes around them?
I'm a bracket on the 9 halves.
Nice. Bracket, because it's an actual point of the graph. It's the lowest point of that parabola. And then the 9 halves. The infinity is the parentheses. Questions? So hopefully tonight's homework is fairly straightforward.
You have 5 graphs. Please show a little bit of work finding all that information. So you're gonna find the same information we just did for the 5 graphs. And then there's a handful of other problems that you'll have to do. And then tomorrow we'll just do like 2 problems involving this variant at method.
Is that the book?
No, it's over here on the counter.
Okay. So I can actually do it.